Well, thanks, everybody. My name is Keaton Strongman. I'm a PhD candidate here at Laurentian University working with Metal Earth. My research focuses on endowment in the Onaman-Tashota greenstone belt. And so I'm going to be presenting a research talk right now, which is partially an update, but also really a synthesis research talk on the topic of the third paper of my PhD, which is the influence of Mesoarchean crust on metallogeny and geodynamics. And we're going to look at some examples from the Onaman-Tashota greenstone belt. So this research really comes back to the central problem of Metal Earth, and that's that Archean greenstone belts have variable metal endowment. Despite having similar, or at least roughly similar volcanic sequences, similar timing, similar structural patterns, we have orders of magnitude difference in endowment between different greenstone belts. And this really points to either a process or a feature that's happening at the greenstone belt scale, or possibly the subprovince or province scale. And so we need to really think about this to try to solve this issue. I think that part of the reason that we're still working on this is that the less endowed belts really have received a lot less love. Research in the past and even currently really focuses on well-endowed greenstone belts because that's where the mines are, that's where the companies have the research funding supplied to us that we can go and study them. And so we look at where the mines are and what features they're related to, and we draw conclusions from there. But what we really need to do is focus on closing the loop and look at the less endowed belts as well and figure out whether or not we see the same features or different features. And that's where the Onaman-Tashota greenstone belt comes in. I would argue that it's really the perfect candidate for a less endowed belt. If you look at here, I'm just going to try to switch to the pointer. Well, either way, you can look at it right here and you can see that it's very easy to access. There are roads running through it. And it has no producing or historical base metal mines. It also has only limited gold production from small historical mines. But despite this, there's a whole series of occurrences throughout this, many of which are what we would call atypical or unconventional, particularly for the Archean. And so we need to start thinking about what the fundamental differences are between this belt, other more endowed belts like, say, the Eastern Abitibi, and whether or not we can identify these. And so right off the bat, we can start by just looking at the map and come up with a few differences. So the first thing you see is that there's just an overall smaller volume of volcanic rocks within this belt when we compare it to something like the Eastern Abitibi, both in absolute space and also relative to felsic intrusions into plutons. So this map is zoomed in at the greenstone belt, but if we zoom back out, the entire area around to the east and west of this is plutonic rocks. And so this is really just a sliver of volcanic rocks within plutonic rocks. We also see a much greater abundance of felsic and intermediate volcanic rocks in this belt. So in the south here, we have a large package of intermediate rocks. And in the north, we have massive packages of felsic volcanic rocks. And that's not really common when we look at places like the Eastern Abitibi. We also have a lack of ultramafic rocks. There's only a few outcrops in the entire greenstone belt mapped of ultramafic material, both intrusive or extrusive. So that's really a striking difference. And when we plot the chemistry of these rocks up, particularly the felsic rocks, we see some odd things. One is that we have no rocks in the F2 or in the F3 field rather, and only a few in the F2 field. The majority of the felsic rocks fall in this F1 field. Which of course is indicative of felsic melts generated with garnet as a residual phase. So these are melts generated at deep crustal depths. We also see contaminated neodymium and hafnium model ages throughout the belt. So this is the entire Wabigoon, but if we take a look here, this blow up is the Onaman-Tashota greenstone belt. And the belt itself is roughly 2.74, 2.73 in age, at least the majority of the volcanic rocks. And yet, when we look here, the model ages are almost all older than that. And we have a dominance of, particularly in this area here, of much older model ages, well into the Mesoarchean. And this really comes down to that final point that I'm trying to make, and the point that the talk revolves around, and that's that there's a wide age span of volcanism in this belt. So there are 4 episodes that we've defined here, 2 in the Mesoarchean and 2 in the Neoarchean, where the majority of the volume of the belt erupted during this episode, the Willett episode, between 2740 and 2719. But the presence of this crust is striking, and many other greenstone belts, particularly like our comparison with the Eastern Abitibi, do not have these features, these wide age spans of volcanism, isolated pulses of volcanism. And I think that really this is the key to everything. And I'm kind of giving it away up here with my title, but I believe that you can explain actually a lot of these differences, including metallogeny, at least in part, by the fact that the majority of this crust, or the Neoarchean crust that is underlain by Mesoarchean material, both volcanic and intrusive. So we do have some direct evidence for this. We saw the contaminated model ages throughout the entire belt. We saw the actual physical expression of Mesoarchean crust on the surface in the belt. So we know that crust is there. And when we look at our seismic transect, we see an abundance of these horizontal reflectors underneath the greenstone belt. So this is the Onaman-Tashota greenstone belt up here on surface along our transect. And just in orange here, we've highlighted what we believe is mid-crustal basement material. And it's defined by these wide horizontal reflectors. And we can see that these underlie the majority of this portion of the belt. And we think that this is probably Mesoarchean material. So what about some of these other features? Well, we can explain a lot of these in the context of underlying Mesoarchean crust. Now, the first off, if we look at the volume of volcanic rocks, especially relative to plutonic rocks, that tells us that we must be storing a lot of melts and making plutonic material. And that's indicative of density filtering. And we need fractionation as well to make the intermediate volcanic rocks. And both of these are supported by, or rather are induced in part by thickened crustal sequences. And so particularly those containing both TTGs and mafic material. And this thickened crust is obviously supported by those F1 volcanic signatures as well. If we think about how this might affect volcanic ratios of mafic to felsic volcanic rocks, that's also conducive to a thickened crustal setting in which rifting is actually inhibited. So you have much more immature rifts, you're generating a lot less mafic material, melting the upper mantle a lot less, and plumes themselves may be stalled or deflected to thinner crustal sequences. That much is not abundantly clear here, but certainly we don't have many ultramafic rocks here, and we need to explain that some way. And this is a way that we can in part explain that. And this the inhibition of rifting and the generation of deeper melts is also a way to explain these F1 felsic signatures. So the hypothesis we're going to talk about today, and really the hypothesis that we're working on my third paper and in a large part of the research that we're doing in this belt, is that Mesoarchean crust strongly influences the geodynamics of Neoarchean assemblages, both their volcanism and through the influence on their volcanism and geodynamics and petrogenesis, their metallogeny. We're going to look at two examples. We don't have enough time to do the whole belt, but we'll look at two key assemblages that are probably some of the best evidence for this difference. So we'll start out with the Elmhirst-Rickaby Assemblage. This lies along the southern margin of the belt. So here's a map of the belt right here that we saw before. BGB is down here, the Quetico, the English River is up here. So this is the belt itself. And here's the Elmhirst-Rickaby Assemblage right along its base. So that's a blow up of this area here. And the Elmhirst-Rickaby is 2740 to 2734 million years in age. And it's in structural contact with the other assemblages and with the BGB to the south. So if you look here, this is the Paint Lake Fault right here, and that's the BGB to the south, and we're in structural contact on all other sides. This assemblage is comprised of pillared mafic flows and andesitic volcaniclastic rocks. It's calc-alkaline and we believe comagmatic, and we'll see some evidence for that in a little bit. But it's quite strange in having a massive section of calc-alkaline basalts, which is a little bit less common than well, it's a little bit uncommon in the Archean. And this large package of andesites here, which contain phenocrysts and we believe are true arc-like andesites, is in fact one of the largest packages of intermediate rocks, volcanic rocks that is, in all of the Archean. So it's quite special. And it hosts numerous atypical occurrences, as you would expect for an uncommon assemblage. We're going to look at one, the Ishkoday, a little bit later, but there's actually a whole bunch of these atypical occurrences that we've looked at. So we'll go over the stratigraphy first. You don't need to worry about trying to read the text on the right. We'll walk through the formations, but we've essentially divided it into two informal formations with a whole number of informal members contained within those. So we'll start out here by looking at the Castlewood Formation. This forms the base of the sequence, and it's dominated by mafic flows. We can see massive and pillowed mafic flows, flow top breccia within them, and two intermediate volcaniclastic members interlayered within these. As I said before, this entire sequence, including the mafic flows, is calc-alkaline in nature, and curiously, it actually becomes more andesitic as we move up through stratigraphy. In fact, the Calvin Lake member up here is basaltic andesite in trace element composition. So if we take a look here at, this is an example from the Castlewood member, we can see nice pillows here, hyaloclastite in between them. That indicates a subaqueous setting, and the dominance of flows in this sequence likely indicates some sort of subaqueous mafic shield style volcanism. So building a low relief, low angle shield style volcano. If we look at the overlying formation, the Rickaby Formation, we see something very different, and that's a complex pile of volcaniclastic rocks, which you can see here, all the way from andesite through to dacite and possibly even rhyolite and trace element composition. And again, we have that general fractionation from the bottom to the top. It's not perfect, but generally we have more mafic material lower and more felsic material near the top of the sequence. We also have a dominance of coarse volcaniclastic rocks, as I said before, over flows, and these are really proximal volcanic units. They're true pyroclastic flows in a lot of cases. We have actual vitric lapilli, both wispy and blocky vitric lapilli, which indicate hot deposition and the fact that these may be primary units. But curiously, right at the top here in the Kenty member, we have dacites that have spine-like structures that appear to be similar to the ones we would expect in a subaerial setting. And we have these breccias overlying them, which contain sub-rounded fragments and scoured bases, which we are taking or interpreting to represent subaerial exposure and constructive volcanism. So uplift, constructive volcanism, and erosion of that volcanic edifice. And because these are all proximal deposits, we believe that this is probably a constructive feature, something similar to a stratocone or a stratovolcano built on this shield. And so, well, this is not what we expect in the Archean. Exactly. We expect more felsic melts. We expect bimodal volcanism. And so this is quite strange. And the chemistry shows this pattern as well. Instead of a bimodal distribution in trace element space, we see a continuous fractionation trend in trace element space from basalt all the way through to rhyolite. And this is consistent with fractional crystallization. And importantly, we have the phenocryst assemblages that support this. We have plagioclase, we have relict amphibole, abundant magnetite. No olivine, unfortunately, but it's quite possible that was destroyed during metamorphism. When we look at their spider diagrams, we can see a calc-alkaline profile, and they all have the same calc-alkaline profile, which is curious, and roughly the same trace element abundances, which indicates recharge from the mantle throughout this process of fractionation. So this indicates here that these are likely, we believe, comagmatic, and possibly may have a metasomatized mantle source, as well as the possibility of some contamination. And we see both of those on this trace element diagram here from Pierce in 2008. We can see here that these values are shifted off of the Morb OIB line, which indicates that the primary melts possibly originated from metasomatized mantle. We have some fractionation along this line that we would expect, but we also have a vertical trend upwards towards average Archean continental crust, which likely indicates contamination. And so what does all of this mean in terms of geodynamics? Well, these really are arc-like units, arc-like volcanism, arc-like petrochemistry. Whether or not it's a true subduction like arc is really at this point kind of splitting hairs, but certainly we have a setting here where we have assimilation fractional crystallization being a dominant process. And possibly some evidence for mash processes to create more arc-like andesites. And so we need to think about what might the Mesoarchean crust do to this portion of the belt? How might this allow you to create this setting that's not actually that common in the Archean. It's not that common to generate these truly andesitic melts. And so if we imagine that, and we know that there's Mesoarchean crust under here based on the isotopes in the seismic line, so we can imagine that this would contribute to stabilizing the crust and providing a density contrast that might allow you to initiate some form of subduction or subcretion, however you want it to work. But you can also imagine here that a thickened crustal sequence would prevent melt ascension and promote storage. So promote this underplating, ponding, and assimilation and storage possibly within the crust here. And that may be one of the key effects here of the Mesoarchean, is to contribute to an arc-like setting in the south. And so that should be associated with non-typical Archean bimodal mineralization. We don't expect VMS in that kind of setting, and that's exactly the case. We don't find VMS here. Instead, we find deposits that are admittedly quite strange, but they bear some resemblance to porphyry epithermal spectrum deposits. So we have multi-generational, very nicely comb-textured quartz vein stockworks at the Ishkoday deposit. And here we have later actinolite magnetite filling these veins. So this is really strange. And this is calc-sodic alteration, really, true calc-sodic alteration, calcium and sodium addition. And although this isn't your typical porphyry or your typical epithermal system, we've got base metals here, we've got odd alteration. It's definitely consistent with deposits within that spectrum. And so we believe that this difference is in part due to the difference in volcanism and geodynamics in that area of the belt. So what about the northern end of the belt? That's the Marshall Lake assemblage. And this assemblage is also very strange, particularly in the Archean. You can see here, this is the belt again. This is the northern margin up here. And this whole area is the Marshall Lake assemblage. So it's a massive assemblage of felsic volcanic rocks along this northern margin of the belt. And it's 2734 roughly in age. Again, it's structurally bound with the other assemblages. But here we have felsic volcaniclastic rocks as the dominant rock type with subordinate flows, all with, again, calc-alkaline F1 dacite to rhyolite-like chemistry and trace element space. And again, here we have atypical mineralization. It's not epithermal-like in this case, it's VMS-like, but it contains odd characteristics that we're going to see in a second. So it's always lags a little bit. There we go. So we'll take a look at the stratigraphy here. Again, don't worry about looking at it right now. We'll go through it in a second. But essentially, we have volcaniclastic rocks dominating the lower portion and flows dominating the upper portion. So let's take a look at the lowermost formations. That's the Grip Lake, Camp, and Marshall Creek formations located here at the base of stratigraphy. And these are dominated by felsic tuff, as you can see here, massive felsic tuff and lapilli tuff and rare tuff breccia. And all throughout this sequence, there's strong alteration, but we still have some evidence of juvenile fragments. Again, wispy lapilli that we're interpreting to represent flattened pumice that indicates that these were likely primary deposits, or at least they were syneruptive deposits. And we believe that, and as well, they're intruded by felsic synvolcanic dikes, possibly a cryptodome in one place, and interlayered with some felsic flows up here in the Camp Formation. And so we believe that this is similar to the kind of explosive pyroclastic succession that you would see in a caldera collapse or an intercaldera ash flow tuff-like setting. It's difficult to prove anything as a caldera. There's quite a long list of criteria, and the amount of mapping up here is just not sufficient to prove it one way or another, but certainly this is consistent with that interpretation. The overlying portion of stratigraphy, the Deeds Island and Eagle formations, are dominated by felsic flows and domes, and they have minor interlayered felsic volcaniclastic units. These are mostly monolithic breccias that lack the juvenile fragments that we saw before, but in the flow top breccias, which are much less altered in this portion of the sequence, we do see rare hyaloclastite that likely indicates that this was mostly subaqueous volcanism. So one way to interpret this is that this might be the volatile depleted style of effusive felsic volcanism that we commonly see associated with caldera resurgence, and possibly some of these heterolithic breccias may be related to either dome collapse or possibly even rim collapse. And so we're envisaging some sort of scenario like this where we have post-caldera resurgence and lava domes. So what about chemistry? Well, we have something, again, not common in the Archean here, basically monogenetic felsic volcanism. And this indicates extensive melting of likely a mafic source with no associated mafic igneous activity. So this is a bit strange. Normally we have bimodal volcanism. Here we have just felsic volcanism, and that's quite interesting. Again, it's all calc-alkaline in nature. It shows, which could be due to crustal contamination. It's also possible that's due to hydrous melting. Both are plausible in this scenario. And again, we have that F1 character, some rare samples here that plot just outside of the F2 field, but likely this indicates a relatively deep melt source, either within or just above the garnet stability field. Certainly no F3 rhyolites here. And so what kind of geodynamic model would this indicate? Well, it's likely that this indicates some sort of immature crustal rifting setting. You're melting hydrous mafic crust likely, and possibly you're contaminating with TTGs, but you have no mafic material reaching the surface. So how might the Mesoarchean affect that? Well, here it's very easy to imagine. Here is where we have the most contaminated isotope signatures and where we believe the Mesoarchean is thickest underneath this portion of the belt. So we believe that thick, stable Mesoarchean crust has inhibited extensive rifting here, favoring those deep melting sources. And that's why you have those F1 signatures. Again, we have a density filter here. Likely you have felsic and mafic material in that Mesoarchean crust. This is promoting underplating, restricting the ascent of mafic melts so that you cannot erupt them as mafic volcanic units. And likely hydrous, it's likely that this crustal material was hydrous, and this could promote flux melting and generate those calc-alkaline signatures with or without contamination. And so what about mineralization? Well, we'll close off here by looking at Marshall Lake. There's a number of occurrences here, and they're very similar to your traditional VMS or volcanogenic massive sulfide. We have pyrite and chalcopyrite-rich lenses. You can see a lens right here exposed on surface, plunging towards the camera here, and a stringer zone running up into it. But associated with this is aluminosilicate assemblages, which really represent advanced argillic alteration, or at least extensive acidic leaching, because here we have, kyanite and quartz rich rock with no other minerals present. So that's atypical for VMS. Excuse me, but can be explained in the context of either boiling in a more shallow water setting or magmatic volatile input into the system, both of which would be roughly consistent with this kind of geodynamic environment. So in conclusion, we believe that there's initial evidence to support this hypothesis that the Mesoarchean crust has at least resulted in very different volcanic assemblages in these two packages than what we normally see in a bimodal mafic dominated and ultramafic dominated greenstone belt, like the Eastern Abitibi that is typically well endowed. So we believe that you can explain these differences in part by underlying Mesoarchean crust, which would have affected the geodynamics, the resultant volcanism, and the mineral deposits of the Neoarchean assemblages. And so going forwards, this is the focus of our research. We're trying to continue this, trying to reinterpret and refine our seismic section and continue looking at the different volcanic assemblages and the mineralization to see if this holds up throughout the rest of the belt. And that's it for me. Thanks. I'll take any questions if there are any, if we've got time.
Well, thank you, Keaton. That was a fantastic presentation for us here. I'm going to take the prerogative and ask a question. I have the controls. The Onaman-Tashota is, as you're saying, is poorly endowed belt, but immediately to the south is Beardmore-Geraldton, which is, it's a thin belt, but it's a very highly endowed belt. What's the relationship between the two, and is Beardmore-Geraldton also underlain by older crust?
So I'll go back to the seismic line here. That's a good question. I'm not exactly sure, but I think this partly can be explained in that context, in the context of underlying crust. The seismic section, we believe we're actually, this is an older interpretation, so we're looking at it a bit more here. And you'll notice that we're not actually sure that this Mesoarchean crust is present underneath the Beardmore-Geraldton belt. We don't see quite as many horizontal reflectors here. And so we've just started going back through this again. And so that could partially explain it. Again, the idea is that these structures originate as, orogenic structures rather, originate as normal faults. And so when you're talking about endowment, particularly in the BGB, it's mostly orogenic gold, not VMS or epithermal. And that is certainly a difference. The Onaman-Tashota belt also doesn't have any epithermal or any orogenic deposits rather. And I believe that could be partly explained in this context. If there is less Mesoarchean crust here, you may have had more effective rifting initially to generate those structures, which might have contributed then to them being deeper structures that reach further into the mantle and have larger fluid reservoirs. But other than that, the other major difference is just a difference in tectonics. Let's see if I can bring up a map of both belts here. Where do I have one? It's going to lag a bit on me here. Yeah, so here we can sort of see it. And we have a dominance of this dome and keel structural pattern up here in the Onaman-Tashota belt, whereas the Beardmore-Geraldton belt is all linear, parallel, thrust-bounded shear zones that are now vertical. So this may play an important part, although we're still not exactly sure what part that is. We think that difference in structural style is also probably pretty important to that.